Okay, we are in section 3.5, which is implicit differentiation. I want you guys to remember a couple things. There's a difference between d dx and d dy. d dx is an operator that instructs you to take the derivative and treat x as the variable. d dy is an operator that instructs you to take the derivative and treat, this time, y as the variable. So if we had d dt, it'd be treating t as the variable. So down here there's an example, there's 4, and if you notice, same exact expression that we have, however in terms of x and some are in terms of y. And then out in front of him you'll notice that there's a d dx or a d dy telling you what to take a derivative with respect to. So let's go ahead and start at b. b says take the derivative with respect to x of 3x squared. This just involves us using the power rule. So we would take 2 times 3 is 6x. Likewise, if you look at c, this says to take the derivative with respect to y. Well, that's my variable here, just like x was the variable over here. And so this is going to become 6y. Now the issue is, if you notice with a and with d, it's asking you to take the derivative with respect to x. However, this is not in terms of x, it's in terms of y. And we don't know if y is a function in terms of x. So what we're going to do is we're going to go ahead and use the same exact power rule. This is going to become 6y. But I don't know if y is in terms of x somehow, maybe enlisted in it somewhere else. So we're going to multiply by dy dx. So the derivative of y with respect to x. So let's go ahead and try d. This says d dy of 3x squared. So again, taking the derivative like normal. And we are going to have 6x times, I'm going to take the derivative of x with respect to y. So this time dx dy. Again, implicit differentiation is going to be used throughout, and it is a challenging topic. So more practice, the better off you will be. So go ahead and give explicit functions and implicit functions stars. And explicit function is a function which the dependent variable can be written explicitly in terms of an independent variable. For example, y equals f of x. If you notice, y is isolated. And an implicit function is a function relation in which the dependent variable is not isolated or on one side of the equation. So if you look at, there's examples of both. The example of an explicit is y equals 3x squared minus 2x plus 1. And this is an explicit function. And this is easy to take the derivative of. We've done this before. Y prime equals, and it's going to be 6x minus 2. So 6x minus 2. And new pencil. And then when we have an implicit, you notice here the y is not isolated. Yes, in this case you could rewrite this and take the derivative, and solve it to make it be explicit, make y be by itself. But we're going to just say this is what we're going to be dealing with. A lot of times you cannot isolate one of the variables, isolate y. So we have an example down here. And it says given 2x squared plus y squared equals 4, find dy dx. So I want you guys to realize it's dy dx. This means we're going to be taking the derivative with respect to x. So if you look at the first term that we have here, it's 2x squared. With respect to x, that's the same variable that we're talking about. So that's just going to become 4x plus. Now, this time taking the derivative of y squared with respect to x, that's not the variable that we have here. So this is going to be 2y times the derivative of y with respect to x, which is dy dx equals, And whatever you do to the left side, you also have to do the right side. So I took the derivative of this with respect to x, so I have to take the derivative of 4 with respect to x, which is just 0. From here, we need to isolate dy dx. That's what you would do up here as well. It's just that it was nicely done in all the previous derivative problems that we've had because y's already been by itself, and it wasn't down here. So I'm going to subtract 4x. And then divide by 2y on both sides. And simplify that. And this is our derivative. So if we were asked to find a second derivative, we could take this and do this whole process all over again. So note down here, this is something really good to look at. We can solve this implicit equation for y. So we could have solved for y up here at the very start and arrive at this at the top and the bottom of a unit of a circle with respect. However, some equations cannot be easily written in explicit form. Thus, we need to use this method of implicit differentiation. So if you had rewritten this and you took a derivative, you'll notice that you can look through the steps are all typed out here, but you would arrive at the same answer that you had up above using implicit differentiation.